Hello viewers, welcome to my channel. This is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College for Women, Nalgonda. In the present class, now I am going to present the topic Electromagnetic Induction, Lecture 1. This is BSc Physics 5th semester, Electromagnetic Theory, Unit 3 syllabus. The plan of my talk is Introduction, Electromagnetic Induction, Faraday's experiment. After that, Faraday's laws of electromagnetic induction, and also we will discuss the integral form of Faraday's law. Next, differential form of Faraday law. After that, Lenz law and explanation. Lastly, we'll see the summary of the lecture. So coming to the introduction part, first let us start our discussion with magnetic flux. What is the magnetic flux? Magnetic flux is nothing but the number of magnetic lines of force passing normally through the given closed surface area, right? So in the figure, if theta is the angle between uniform magnetic field and the normal drawn to the small area A, then the flux through this small area element is given by phi equal to the dot product of magnetic induction field strength and area vector B bar dot A bar, that equal to BA cos theta. Okay, so this is the small area element A bar. The direction of magnetic field is B bar. So here magnetic lines of force indicates the direction of B bar. The normal drawn to this area element is n cap, right? That is since area is the vector quantity, the direction of area vector is along the direction of n cap. Here the angle between n cap and B bar is theta. Then the magnetic flux through this area element is given by phi equal to B bar dot A bar, that equal to BA cos theta. You can write it as B cos theta into A. So what is B cos theta? B cos theta represents, it is the normal component of magnetic field strength. Magnetic field strength along the perpendicular to the area vector. Perpendicular to the area vector. Perpendicular to the area, not or parallel to the n cap direction. So B bar component, B has two components, B sin theta and B cos theta. B cos theta is the component which is perpendicular to this plane or the direction of A bar. Okay, so the product of normal component of the magnetic field and area gives the magnetic flux through the given surface area. Okay, so that is, it is defined as the product of areas surface and the component of magnetic field normal to that surface. This is the magnetic flux. Since we have taken the dot product of two vectors, we know that the dot product of any two vectors represents what? Scalar quantity. Therefore, magnetic flux is a scalar quantity, right? Because here we count the number of lines of force crossing perpendicular to the given closed surface area. Since we are taking the magnitude or only numerical value, it is very clear that the flux is the scalar quantity. The SI unit of flux is Weber and the CGS unit is Maxwell. 1 Weber equal to 10 power 8 Maxwells. Okay. Now, the flux through the coil can be changed by changing one or more of the following factors. So the flux through the given closed surface area can be changed through this changing of following factors. By changing the magnitude of B bar, by changing the angle between area vector and magnetic field strength, or by changing the magnitude of the area of the coil, or the number of turns in the coil. So by changing any one or these four physical quantities, four physical parameters, we can change the magnetic flux through the given coil. Okay. Now, so actual our discussion is electromagnetic induction. So what is electromagnetic induction? What is EMF, induced EMF, induced current, and Faraday's laws? All these things now we will discuss here. Up to 1820, Eiersted, up to 1820, what we believed is electricity and magnetism are different. They have no relation. But after the discovery of Eiersted, that is, when the current is flowing through the conductor, the magnetic field is forming around the conductor. So this is the result of Eiersted experiment. So due to this result, the magnetic needle, which is kept near to the current carrying conductor, will deflect, right? So with that experimental observation of Eiersted, so it is believed that there is a relation between electricity and magnetism. Okay. So up to that experiment, up to the invention of Eiersted experiment, we believe that so that there is no relation between electricity and magnetism. So after the Eiersted experiment, we concluded that there is a relation between electricity and magnetism. So therefore, due to the current carrying conductor, or when the current is flowing through the conductor, the magnetic field is forming around the conductor. So the quantitative analysis was given by Ampere, right? That is the observation, after the observation of Eiersted experiment, the quantitative analysis, that is the magnitude of magnetic field strength, was explained by the Ampere. In the same decade, around 1831, Faraday discovered the converse effect of this Eiersted experiment. What is that? We can produce the electric current from the magnet, from the varying magnetic field. Okay, when the current is flowing through the conductor, we are producing the magnetic field. This is the result of Eiersted experiment. The converse effect, why it is not happens, this is the thought got by the Faraday, and he found experimentally that we can produce the electric current. Electricity can be produced by changing the magnetic flux, which is linked with that closed circuit or closed loop. For that, he done the very simple experiment. So this is a wooden core. So on that, a coil is connected to the battery, and the second coil, this is the Q is the second coil. It is connected to simply the galvanometer, right? So here there is no battery, but in the primary coil, there is a battery. The ends are connected to the battery terminals. So here when the tap key is closed, the circuit is closed, current starts flowing through this primary coil, then suddenly the galvanometer deflects. So when the tap key is closed, then galvanometer deflection was observed. And also when the tap key is broken, then also deflection the galvanometer observed. Okay. So once the tap key is closed and steady current is flowing through this primary coil, then there is no deflection in the galvanometer. No deflection in the galvanometer. So that means, so whenever the changing current is flowing through this primary coil, then the deflection was observed in the galvanometer. So due to this reason, whether tap key is closed or the tap key is pressed or tap key is broken, the circuit, then in these two cases, in the first case, current is increasing with time. The second case, current is decreasing with the time. So when the increasing current or decreasing current is flowing through the primary coil, then due to this, according to Eiersted experiment, the magnetic field is changing. Magnetic field forming around this conductor is changing. So that magnetic flux is linked with this secondary coil. Hence, the magnetic flux linked with the secondary coil is changing due to the changing of current. So therefore, the flux density linked with the secondary coil is changing with the change of current in the primary circuit. Therefore, the deflection is occurring in the galvanometer. And also, he done another experiment. Instead of this wooden core, this was replaced by the iron core. Then he observed the more deflection in the galvanometer. By increasing the number of turns in both the primary coil and secondary coil, then also the quantity of deflection was increased. So when the current is changing, the current is changing either increase or decrease, then the varying magnetic field which is linked with the secondary coil, due to the linkage of varying magnetic field or varying magnetic flux or flux density with the secondary coil, we are getting the deflection in the galvanometer. This is the results. These are the results found by the Faraday in 1831. So this you can understand from this figure also. The second experiment you see here. Here a closed circuit is connected to the galvanometer. There is no battery. Now a bar magnet north pole is pushed towards the coil. So towards the coil. Then the deflection occurred in the galvanometer. In the second figure, here the north pole of bar magnet is moved away from the coil, then also deflection observed, that is opposite to the deflection observed in the first case. So what happens here? So whenever the bar magnet is moving rush towards the coil closed circuit, then an increasing magnetic field is enclosed with this coil. So increasing magnetic flux is linking with this coil, that is producing the EMF electromotive force in this circuit. Hence we are getting the current, that current is called induced current, and EMF is known as induced EMF. In the second figure, here the bar magnet is moved away from the coil, then the magnetic flux linked with this closed circuit is decreasing with respect to time. Therefore, deflection is observed here. Here also we are getting the EMF. So that in two cases, EMF is producing either increasing magnetic flux or decreasing magnetic flux linking with a closed circuit or closed loop. EMF is inducing in the closed circuit. That EMF is called induced EMF, and the corresponding current is known as induced current. So the phenomenon of inducing EMF or current due to the relative motion between a magnetic field and the closed loop is called as electromagnetic induction. So what is the relative motion? Yes. So by keeping the bar magnet constant, you can move the coil here. Then also you can observe the deflection. By keeping the coil constant, you can move the bar magnet either towards the coil or away from the coil. Then also we observe the deflection in the galvanometer. By moving both magnet and coil either in the same direction with a different speed or in opposite direction, then also we'll observe the deflection. So whenever the relative motion between the magnetic field that is forming due to the bar magnet movement and the closed circuit, closed loop, then we are getting the EMF in this closed loop. This phenomenon is called as electromagnetic induction. So that EMF is called as induced EMF, and the current is called induced current. So the direction of this induced EMF or induced current is always opposite to the cause produced in it. So that will explain by the Lenz law. We will discuss that one. In the below figure, here the primary coil is connected to some battery. The secondary coil S is connected to the galvanometer, right? So here, whenever the tap key is closed, by pressing the tap key, then this circuit is closed, then current starts flowing in this primary circuit. So current starts from 0 to steady value I naught value, right? So here increasing current is flowing through this primary coil. So due to that, the magnetic field forming around the primary coil, which is enclosing the secondary coil. Therefore, the deflection is occurring in the galvanometer. In the next figure, here the circuit is broken by means of breaking the key. Then current doesn't comes to the rest at a time. Current starts from steady value I naught to becomes to 0 after some time. In this case also, the galvanometer deflection is occurring. So here decreasing current is flowing in this primary coil. So decreasing magnetic flux is forming around it. So the magnetic lines of force or magnetic flux linking with the secondary coil is decreasing with the time. Therefore, we are getting the deflection in the galvanometer. Okay. So these are the experimental results observed by the Faraday. Okay. Now, so that we can say that the EMF can be produced by changing the area of the loop or changing the relative orientation of the coil with respect to the magnetic field or changing the value of magnetic field. Okay, so these are the three cases, right? So what I am saying is, one is changing the area of the loop. The second, changing the relative orientation of the coil with respect to the magnetic field, or by changing the value of magnetic field, we can observe the electromagnetic induction, right? So based on these results, Faraday proposed two laws. They are called as Faraday's laws of electromagnetic induction. The first law is, whenever the magnetic flux linked with a circuit is changed, an EMF is induced in the circuit. Here the EMF induced lasts so long as the change in magnetic flux continues, right? So the magnetic flux linking with the circuit is changing with respect to time. Then EMF will be induced in the circuit. That induced EMF lasts so long as whenever the change of magnetic flux continues with that coil. This is called the first law of Faraday's electromagnetic induction. The second law talks about the magnitude of induced EMF. The magnitude of induced electromotive force is directly proportional to the negative rate of change of magnetic flux. That is, mathematically, we express it as E equal to minus d phi by dt, where phi is the magnetic flux. Okay, the magnitude of induced EMF is directly proportional to the negative rate of change of magnetic flux with the circuit. So E equal to minus d phi by dt. This is also known as Newman's law. If the coil has capital N number of turns, then we write it as, then the flux phi is equal to, for one turn, phi is equal to AB cos theta. For n turns, the magnetic flux linked with the coil equal to NAB cos theta, right? Or phi is equal to N into AB cos theta, N A bar dot B bar. So from that, for the coil having n number of turns, we write expression as E equal to minus d by dt of n phi b. D by dt of n into phi b, writing n outside, minus n d phi by dt. Okay, let me repeat. If the coil has one turn, we write the magnetic flux linked with the coil how much? Phi equal to A bar dot B bar, that equal to AB cos theta. If the coil has n number of turns, then the flux linked with the coil how much? N into phi b. According to the Faraday's law, E equal to minus d by dt of phi b. Since the coil is having the n number of turns, minus d by dt of n into phi b, that equals to minus n d phi by dt. Okay. Now, so let us derive the expression integral form of Faraday's law. So for that, you consider a magnetic field, a magnetic field around a current carrying conductor, right? Magnetic field around a current carrying conductor. So in that, I am considering a closed surface of any shape. Okay. So the magnetic field strength, its neighborhood of this closed circuit is B bar. Here these arrow marks represents the direction of magnetic lines of force passing through this closed surface. If this total area is divided into very small infinitesimal area elements, each equal to ds bar. The small area element is the vector quantity. The direction of ds bar, we know that is perpendicular to that surface along the unit vector, normal unit vector drawn to that surface area element. So this is the direction of ds bar. So this closed surface is divided into small area elements ds bar, right? Now, the magnetic field strength, the electric field strength along this closed loop at any point this boundary line. So I am dividing this small boundary line into small length elements. Here you can say a small length element dl bar. The direction of dl bar is along the tangent line direction. So here electric field strength is making some angle theta with the dl bar direction. Okay. So what is, we have to understand from this figure. So we are observing or we are considering a closed surface near to the current carrying conductor or a magnetic permanent magnet. So in that magnetic field we consider a closed loop, right? So this total closed surface divided into small area elements, and along the boundary of this closed curve, if it is divided into small length elements, here dl bar direction is like this, and at that point electric field strength direction is E bar like this. Okay, E bar direction like this. Here what we are doing, here we are changing the magnetic flux. We are changing the magnetic flux linked with this closed surface by moving the bar magnet towards the closed circuit, or by moving the bar magnet away from the closed circuit, right? So in any one of that process, we are changing the magnetic flux, which is enclosed with this closed loop, right? Now, the magnetic flux through a small area ds is given by b bar dot ds bar. Therefore, the flux through the entire closed circuit is phi b equal surface integral b bar dot ds bar. This is d phi. D phi equal to b bar dot ds bar. Flux linked with small area element ds is nothing but d phi equal b bar dot ds bar. Then flux through the entire closed circuit is what? Phi equal to surface integral of d phi. That is surface integral of b bar dot ds bar. Say equation 2. So whenever magnetic flux is changed, then the electric field is induced around the circuit according to electromagnetic induction phenomenon. As we observed in the Faraday's experiment, when the magnetic flux is changing, since that varying magnetic flux is enclosing this closed circuit, electric field is induced around the circuit. Therefore, the line integral of the electric field gives the induced electromotive force in the closed circuit equal to closed integral of E bar dot dl bar equation 3. This is the important expression. What I am writing? The line integral of that closed curve, the line integral of the electric field strength along that closed curve is induced electromotive force in the closed circuit. So from equations 1, 2, 3, right? Since E equal according to Faraday law minus a d phi by dt. So here we have equal to what? Closed integral E bar dot dl bar. Therefore, closed integral E bar dot dl bar equals to minus a d by dt of phi. But we have phi is equal surface integral b bar dot ds bar. Substituting that, we got this equation. What is that? Closed integral E bar dot dl bar equal to minus a d by dt of surface integral of b bar dot ds bar. Okay, so that equal to, you can write minus surface integral of dou b bar by dou t dot ds bar. You can write that one. So this is known as integral form of Faraday's law. This equation is known as integral form of Faraday's law. Okay, now, so what is the differential form of Faraday's law? So let us start this derivation with integral form of Faraday's law. According to integral form of Faraday law, we have closed integral E bar dot dl bar equal to minus a d by dt of surface integral of b bar dot ds bar. This is equation 4. This equation represents what? This equation represents that the line integral of electric field strength around any closed circuit is equal to the negative flux through the circuit. The negative rate of change of flux. So you can correct this. The negative rate of change of flux through that surface. Closed integral E bar dot dl bar is nothing but this is the negative rate of change of magnetic flux minus d phi by dt, where phi equal to b bar dot ds bar we substituted. So that is the same equation I have written here. But according to Stokes' theorem, we know that Stokes' theorem related line integral and surface integral. So what is that? Closed integral E bar dot dl bar equal to, you can write surface integral of curl E bar. Curl E bar is del bar cross E bar dot ds bar. Curl E bar means del bar cross E bar dot ds bar. This is equation 5. From equations 4 and 5, you can write surface integral del bar cross E bar dot ds bar equal to minus d by dt of surface integral of b bar dot ds bar. Then by removing the surface integral both sides, you can write del bar cross E bar equal minus dou b bar by dt. So what is that? Curl E bar equal to minus dou b bar by dt. This equation is called as differential form of Faraday's law. Okay. Del bar cross E bar or curl E bar equal to minus dou B bar by dou T. This is known as differential form of Faraday's law. Right. So what is the Lenz law? The Lenz law states that the direction of induced EMF or induced current in a closed loop or closed circuit is such that it always opposes the original cause that produces it. It is based on the principle of conservation of energy. So let us discuss in detail about this Lenz law. The magnitude of electromotive force inducing the closed loop due to the relative motion between the coil and magnetic field was given by Faraday's laws. The direction of induced EMF or induced current was given by this Lenz law. So this is the difference between the Faraday law and Lenz law. Right. You consider that this is a closed loop or closed circuit. A bar magnet north pole is moving towards the closed loop. As it moves towards the closed loop, what we can observe, the more number of lines of force will intersect this coil. So the magnetic flux linked with this coil is increasing. Right. With respect to time, the magnetic flux or flux density enclosing the coil is increasing. Therefore, the magnitude of magnetic induction in the coil increases. The magnitude of magnetic induction enclosed with the coil increases. Therefore, the induced EMF, the magnitude of the EMF induces also increases. But here, one thing you have to observe is, whenever this bar magnet brought near to this closed loop, right, then as electromagnetic induction phenomena taking place, EMF is inducing in this closed loop. Then it behaves like around this closed loop, again the magnetic field is forming. Therefore, it behaves like a magnetic dipole. Here, at the face opposite to this north pole will act like a north pole. Since similar pole is forming opposite to the north pole, that will reflect the bar magnet what is we are keeping near to this one. So there will be a repulsion force between this closed loop and bar magnet. Therefore, we are telling that the direction of induced EMF is opposes the original cause that produces it. Okay. Now, suppose if the bar magnet is moving away from the coil, then the number of lines of force intersecting the coil is decreasing. So the magnetic flux enclosing the coil is decreasing. The flux density enclosing the coil is decreasing. Then here south pole will be formed at this phase. that south pole will attract this north pole. So there exists attraction force between the magnet and the coil, magnet and this opposite face of the coil. Therefore, here also the direction of induced EMF opposite to the cause that is producing in it, right? So that is I am telling here. When the applied flux density in a closed circuit is increasing, that is the case of when the bar magnet approaching the coil, then EMF or current induced in the closed circuit is in such a direction as to produce a field which tends to decrease B bar. As there is existing the repulsion force that will reduce the magnetic induction field strength. Okay. Similarly, when the applied flux density is decreasing, that is the second case. When the bar magnet is moving away from the coil, here the magnetic flux density is decreasing in the magnitude. Therefore, the current in the closed circuit in such a direction is which tending to the increased field, because in that case, as we discussed, their attraction force exists because of the south pole is forming at that face that will attract the north pole of the bar magnet, that will increase again the magnetic flux. Hence, the induced current is in a direction such that it produces a magnetic flux tending to oppose the original change of flux. Okay. Therefore, the phenomenon of inducing EMF in a closed circuit due to the relative motion between the coil and magnetic field is known as electromagnetic induction. So with that explanation, the final conclusion, what we can say is, if there is a relative motion between a magnet and the closed loop, then the EMF can be induced in the closed loop, right? The direction of EMF, the direction of induced EMF or the direction of induced current is according to the Lenz law. It is the consequence of law of conservation of energy. Right. So the methods of producing electromotive force, we can say from the previous discussion that by changing the area of the lobe, we can change the magnitude of EMF. By changing the relative orientation of the coil with respect to the magnetic field, by changing the value of magnetic field. In these three parameters, by changing any one or both three parameters, we can change the EMF producing in the coil. Right. So in the present class, what we discuss, if you see the summary of the present class, so whenever the magnetic flux linked with the circuit is changed, then EMF will be induced in the circuit. That EMF induced is called as induced EMF. This induced EMF lasts so long as the change of magnetic flux continues in that closed circuit. This is the first law. The second law represents that it talks about the magnitude of induced EMF. What is that? The magnitude of induced electromotive force in the closed loop is directly proportional to the negative rate of change of magnetic flux linked with the circuit. So that is, mathematically we write E equal to minus d phi by dt, where phi is the magnetic flux, minus d phi by dt is the negative rate of change of magnetic flux. Okay. After that, we discuss and derive the integral form of Faraday's law. Integral form of Faraday's law mathematically can be expressed as closed integral E bar dot dl bar equal to minus d by dt of surface integral of B bar dot ds bar. Okay, so that is what, that is the line integral along the curve of closed loop, the line integral of electric field strength along the curve of closed loop is equal to the negative rate of change of magnetic flux minus a d phi by dt, that is called minus a d by dt of surface integral of B bar dot ds bar. And also we derive the differential form of Faraday's law by using the integral form of Faraday's law. Okay, so what is that? The curl of electric field strength. The curl of electric field strength generated due to the induced EMF is given by curl E bar equal to del bar cross E bar, that equal minus dou B bar by dou T, that is minus dou by dou T of magnetic field strength. Okay. The Lenz law states that the direction of induced EMF or current in a closed circuit is such that it opposes the original cause that produces it. Okay, it is based on the principle of conservation of energy. Why? Because so in that experiment, as I told you that when the bar magnet is brought near to the closed loop, then repulsion force is existing. Against the repulsion force, there we have to do some work. The work done by the external agency is in the form of energy. So their energy conservation is obeyed. Similarly, when the bar magnet is moving away from the closed loop, then attraction force exists because here you can understand that, say for example, this is a closed loop, it is a bar magnet north pole, right? So here the north pole of the bar magnet is moving towards the closed loop. Then this acts like a, as the magnetic field due to this bar magnet, the magnetic field due to this north pole is intersecting this coil, intersecting this closed loop, right? So therefore what happens? Then electromagnetic induction takes place, then EMF induces and the current induces in this coil. Due to the flow of this induced current, again its own magnetic field forms around this coil, right? So then it behaves like a magnetic dipole. Here, this phase, since it behaves like a magnetic dipole, then the phase opposite to this north pole, that is this phase acts like a north pole, then opposite phase, then another phase acts like a south pole. So when the north pole is brought towards the closed loop, then this phase will act like a north pole. Since like poles are existing, like pole there exists repulsion force, then against this repulsion force, the work has to be done. Similarly, when the north pole is moving away from the closed loop, then this acts like a south pole. Then that will attract the north pole. Therefore, here also against the attraction force, the work has to be done. Therefore, it is the consequence of law of conservation of energy, that is you have to understand from this. Okay. Thank you.